Also, I need to get the recording going. So here we are. Now we're being recorded. So once again, exam 3 will be this Wednesday, and already kind of talked through that. Anybody got a question about the exam? Okay. Recordings of our sessions are available. I failed to start the recording last Wednesday, so nope, there's none of that one, but there is tonight, and there was of last Monday. So those are available. You go to course materials, collaborate recordings, click on the date of the one you want to review. So that would mean that you would go over here to course materials, and then you'd click on collaborate recordings, and then it's going to take you to YouTube. I would recommend that you click on the link, not where it says watch video, because you'll get a full screen over here with clicking on the link, and then you can save it into your YouTube. Transcript of the text, or the chats, I'm sorry, the chats will be in this link here, so you can click there and you download that. And somebody said something. Let's see what they said. Yeah, I do have the answer sheet for the buffer. Let's see. Sorry, I didn't think to put that up. Okay, so now you have a link to the key for the buffer worksheet. Yeah, sorry I didn't do that earlier. Anytime if you're not seeing something like that, shoot me an email or a text message. Oh yeah, I've already been there. Now let's look at, oh yeah, 14B, and I don't know why it's saying that. That looks really weird. Anyway, that particular assignment was extended. Okay, if you're having internet connection issues, I already mentioned this. The school announced this. If you're having trouble, not a perfect solution. Anyone does not have access to Wi-Fi, they are welcome to utilize the college's Wi-Fi from their parked car on the west side of campus. Access to the parking lot is available from Palmer Street entrance. It's near the M building. When parked, this is what I added in, remain in your car, maintain social distancing, don't have a party in the parking lot right now. It would probably be a bad idea. But anyway, that's not going to solve your problem if you are confined to home, though. So I don't know what to do for that one. If you're having issues with your computer itself, having a computer with a camera and a microphone is essential for participation in online instruction during the remainder of the semester. If you do not have regular access to a reliable computer, the college may have a solution. So this would be on Wednesday. Complete the online request. I would do that as soon as I could, because I'm sure that there's more people needing these than there are computers. Then the next student laptop distribution is going to be Wednesday, April 8th, 1:30 to 4. And you know, if you do the online request, they're going to tell you where to come for that. Also, if you're having other issues with your computer at home, you're not needing a computer, but there's just something not working right, please try to contact the Educational Technology Resource Center or the ETRC at the email over here. I know they've already helped some people that were having some problems making things work, so that's a possible solution for that. Okay. Can't think of anything else right here on Blackboard. I'm going to go to Sapling. So here we are. And let's see, for chapter 14B and 15, the topic introduction and the homework are not due until April 7. We finished that up some time ago, so you guys should be okay for that. And then the topic introduction and homework for chapter 16 is due on the 15th, so that's quite a bit down the road. You should have plenty of opportunity on that. Now, scanning down at other assignments, let me see if there's anything else you should be looking at. Nope, that's pretty much it, is the chapter 14B and 15. So I'm going to stop sharing my screen and ask again if there's any questions about anything. If you want to talk, just raise your hand or you can chat. Okay, then we're going to do a little bit of lecture, and then we'll get on with the lab. So I'm going to share the PowerPoint for. So we stopped at, let's see, find the slide. Okay, we stopped on this slide, but let's see, in the run up to this one, we were looking at the Gibbs free energy equation. So that was back on this slide. Oh, well, let's give it a second. It should be working. I'm just going to give it a minute, see if it works. Jamie, can you still not see it? Okay, I'm going to try unsharing and then coming back in with it. Okay, Jamie, can you see this? Okay, looks like we're all right. So we saw this before. This is Gibbs free energy equation. Oh, what do we got? Still can't see it, but I downloaded the slide so you can tell me what slide number. Okay, that's kind of the hard way for you. I'm sorry. It's number 19. The title is Gibbs free energy. Okay, sorry that you're having to do that. So anyway, the Gibbs free energy equation, at the bottom of the slide, the delta G, that's the Gibbs free energy, and it's equal to the delta H, that's the enthalpy for the reaction, minus then the change in entropy, that's the delta S, and that's multiplied by the temperature, which is going to have to be in Kelvin for it to work out. Going to the next slide, which is going to be number 20. Again, this one's also labeled Gibbs free energy. The top of it has the equation delta G equals delta H minus T times delta S. And this is how you interpret the Gibbs free energy. If the value is negative, then the reaction is spontaneous, and spontaneous going forward, going towards the products. If the Gibbs free energy is 0, the system is at equilibrium, and so it's not going to be, you're not going to have any further reaction. And then if the Gibbs free energy, the delta G, is positive, the reaction is not spontaneous going forward, but it is spontaneous going in the reverse. And then we had a table that put all this information together. And the easiest, let's see, the two easiest ones to understand, let me get a different color going here, is the green square, where the enthalpy, the delta H, is a negative number and the entropy is a positive number. In that case, the reaction is always going to be spontaneous going forward. And then the other one that's pretty easy to work with is the red square, where the enthalpy is going to be a positive number, the entropy is going to be a negative number, so the Gibbs free energy comes out being positive, and that reaction is never going to be spontaneous going forward. It will be spontaneous in the reverse direction. And then the other two cells in this matrix is where you have both values positive or both negative, and then how that comes out depends on the temperature, because the temperature will either make the entropy more important or less important. If the temperature is a big number, it's going to make it more important. If the temperature is low, a small number, it's going to make the entropy less important. Okay, so that's how far we got last time, and then let's go on to this. This is what's called, this is slide number 2. These are the standard free energy changes. So these are the standard Gibbs free energies, is what this is. And you had something similar to this when you had the thermal chemistry chapter in Chemistry 140, first semester General Chem. But in that case, we were looking at the delta H, or the enthalpy, and there's standard values there. So the same rules apply that applied to the enthalpy. That is, that you're forming something, so you're going to form whatever it is from elements, and those elements are going to be in what is considered to be their standard elemental form. So for instance, carbon is going to be a solid, and it's going to be in the form of graphite, not diamond. And that's the most common way to find carbon at room temperature 25 degrees C and 1 atmosphere pressure. Oxygen is going to be O2 gas, and that would be the most common way to find it. Hydrogen would be H2 gas. That would be the most common way to find that. So the thing you have to consider is what's the most common form of that element, and that's what you're going to use in one of these reactions. And then also this requires standard conditions of 25 degrees C and 1 atmosphere. But the biggest thing that affects how this goes is that the product has to be only 1 mole of product. It cannot be some other value in the coefficient for the product. So of the reactions that we're looking at here, the one that's going to point this out is where we are forming water, H2O. If we were going to write out the reaction for forming water, what we would normally do is something like this. We're going to form H2O, so I'm going to put the formula for that out here, H2O. I'm going to make it a little bigger so we can see it, and move it over because we're going to need some space. And then I'm going to put an arrow in there for that. So, because we're going to write a balanced equation. Sorry, this thing's a little awkward for writing stuff. So I'll move that over, and then we're going to make water from oxygen gas and hydrogen gas. So we'll do the formulas for those. So I'm going to have O2, and then I'm going to have H2, and then I'm going to need a plus sign in there. So go through and make all those larger so we can see them a little better. And then after we get all of the different elements that we need to make H2O, then we look at the equation and it's not balanced. Because in our equation, we've got oxygen is O2, oxygen in the product water is only 1 oxygen. So we would need to add a coefficient of 2 to the water. So I'm going to do that now. And when I do that, we're going to need a coefficient of 2 on the H2, the hydrogen. So I'll go ahead and do that also. And then again, I'll make them bigger so you can see them better. And now the equation is balanced. We got O2 plus 2 H2s produces 2 H2Os. The equation is balanced. But we have a problem, and that problem is that the coefficient on the product is a 2. And we said that we can only have 1 mole of product. That's right above the table, 1 mole of product. So that's not going to work. We're going to need to instead have a slightly different equation where we only have we only have 1 molecule of our product. So I'm going to pull that. Oops, I'm going to pull the 2 out of there. Whoops. That's not real easily done. Okay, I'm going to take the 2 away. But now, for this to work, I'm going to need a coefficient of 1/2 in front of the oxygen. So I'll do that. Okay, I was hoping to be able to make an actual fraction, but not going to work, so I'll do it like this. I mean, I am getting a fraction, but not a nice one. So now our equation has to be 1/2 O2 plus H2 produces 1 H2O. So that's the formation reaction for making water. Now the other ones are a lot easier to deal with, because if it was something like, say you're going to make C3H8, you're making it from carbon and hydrogen. Well, when you balance it, you only get 1 molecule of product. Or if we're making carbon dioxide, again, we can make it from the elements and we only get 1 product. So those are not a big deal, but if you're making the water or something like that, we have to end up using fractional coefficients. Now, a couple other things I want to point out here, that is that in the table that we're going to have for formation values, it's not going to include the equation. all it's going to have is what is being formed, so OH2, C3H8, CO2, H2O. It's going to have that, and it's going to have the Gibbs free energy of formation. So that's those values 0, 0, negative 23.4, negative 394.4, negative 228.6. But it's not going to have the equation. And many times that doesn't matter, but for the time when it does, you're just going to need to remember what those equations look like. The main thing being you only have one molecule product. The other thing I need to mention is that in a table of free energies values, you're not going to have it for things that are already in their elemental form. So for instance, for something like oxygen O2, that's not even going to show up in the table. You just need to know that's going to be 0. And for something like H2, that's not going to be in the table either. Just need to know that that's 0. So our next slide will show you what the tables will actually look like. So we're going to slide number 23. So it's blanked out the stuff that would not normally appear. So you're not seeing O2 or H2 any longer. You're not seeing the reactions. You're just seeing what the products are and what the Gibbs free energy value looks like. Okay, I got one more slide here that we need to look at, and that is what do we use these things for? And we'd use them in figuring out the Gibbs free energy for a particular reaction. So I'm on slide 24 now, and what the title of it is standard free energy changes. And we've got a example reaction here. We got C3H8 plus 5 oxygens makes 3 carbon dioxides and 4 H2Os. The way that we figure out the energy, the Gibbs free energy for that entire process is the equation that is directly below that. That says that the Gibbs free energy of reaction is equal to the Gibbs free energies for the products, like we have on the table, and the Gibbs free energies for the reactants, also like we have in the table. Now you notice that there's also a lowercase n and a lowercase m, and those correspond to the coefficients that we have for the different molecules in our balanced equation. So you're going to have the products first, the reactants afterwards, and they're separated by a minus sign. So our first product that we want to consider then is going to be our, I'm going to change colors, is our carbon dioxide. The value of carbon dioxide is negative 394.4. Coefficient for carbon dioxide is a 3, so we're going to multiply that Gibbs free energy by 3. The other product we need to consider is the H2O gas. Be sure you pick, if there's more than one water in a table, make sure you're picking the right one, whether it's gas or liquid or solid. Anyway, the value for that's a negative 228.6, and there are 4 waters in the product, so you have a coefficient of 4 down in your equation where you're calculating the Gibbs free energy. Then we're going to move from the products to the reactants, but in our equation, we see that they're separated by a negative. So everything that follows has to have that negative applied to it. So we got the negative in our equation that we're using to solve this with. And then we've got the, the reactants, not the products, the reactants. And so our first reactant we're going to consider is the C3H8, and its Gibbs free energy is a negative 23.4. There is only one of those C3H8s, so you have a 1 in front of it in our calculation. And then the next thing we have is 5 oxygens. But remember, oxygen's value is 0. We could go ahead and put in the 5, but it's not going to change anything, of course, because you're multiplying it times 0. But again, that zero that we put in to do the calculation would not be in the table. You'd have to know that. And then we're just going to take all those values and simplify it, and we end up with a negative 2074. Now, at this point, there's a question that we need to answer, and that is this going to be spontaneous? According to what we've already heard. Will it be spontaneous? And what we've seen previously is for it to be spontaneous in a forward direction, then it's going to have a negative sign on the number. We don't care how big or how small the number is, just is it negative or positive? And since it is negative, then this is going to be a spontaneous reaction. Okay? Now, has anybody got a question on what we just did here? Okay, we're going to be doing a worksheet on this, but not tonight. Let's see what my next slide is. Okay. Oh yeah. What this next slide is, number 25, is that we're doing the same kind of calculation, but we're doing it in one case for the enthalpy, the H, or for the entropy. Because we can, and we'll see this when we do the worksheet, we can calculate the enthalpies, we can calculate all the entropies, and we can combine them together using the Gibbs free energy. Now, I do need to point out something here. These slides, somehow when Collaborate got the slides, it messed them up. So every place you see a D, that's supposed to be a delta. So I'm drawing on there so you see that. Those are supposed to be deltas. And every place there is a capital S, those are supposed to be a sigma or a summation sign. So, sorry, I don't know why it does it, but apparently it does not know how to handle the Greek characters. So I drew those in for you. Now, I think that might be the last slide, but let's check. Oh, no, we got a table of values for enthalpies and for entropies and for Gibbs free energies for several different materials. Some of this is a repeat of what we had earlier, but then we also have carbon monoxide and we have CH3CO2H. So that's acetic acid. And what we're going to do, see, actually, we're going to use that when we do a worksheet. So we're not going to actually use it for another slide here. Now, I'm on slide number 27, and something has really gone wrong with this slide. Okay, I'll fix it, but it's not right. Okay, you see the equilibrium constant there, the KEQ. Well, it's just kind of out here in the middle of nowhere for some reason. It should really be after the natural log. And what this equation is doing is it's relating this new number that we have gotten introduced to in this chapter, the Gibbs energy to delta G, and it's relating it to the equilibrium constant that we did for the previous 3 chapters. We were doing those over and over again. The main thing to notice here is that there's a negative sign in the equality, okay? And so what that means, if we want to put some words to it, is that there is an inverse relationship between the Gibbs free energy and the equilibrium constant. So that's what the negative is telling us. And that's spelled out here in in the words below. Equilibrium constant is inversely related to the Gibbs free energy. So conditions that make the Gibbs free energy negative is going to give the largest equilibrium constant, which goes with the idea that if you have a negative Gibbs free energy, the reaction is going to go to the products spontaneously. So that finishes up this chapter, but we do have some worksheets to do, and I want to circle back and get those on Wednesday after we get done with the exam. So we'll leave it for that. But again, has anybody got a question about any of this stuff? Okay, if not, then we'll go on and get to the lab. So I'll show you where you can find that at. Share my screen with you. And so here we are. So you should be able to do this too. You look at Blackboard, to switch tabs, one for Collaborate to the one for Blackboard. And you click on Course Materials. And then you're going to scroll down to where you find the lab reports. You click on it. And you should have an item called Oxidation Reduction Simulation. So you're looking for Lab Report 8, Oxidation Reduction Simulation over on Blackboard. Now, if we click on that, you're going to see the assignment for it. And the instructions are follow the instructions on the attached file. That's down here below where it says redox simulation. And then it says, this is a direct link. Well, I'm sorry, I did not remember to link it, so it's not actually linked. But you'll be able to get the link from the instructions. And you're going to submit a report, one per group, with these items, title, date, partners, 4 data tables, one for each activity through 4. Then you're going to have a conclusion, which is going to be on the oxidation order, and you'll see what that means here in just a little bit. And then the other conclusion is hydrochloric acid reactivity. And again, you'll see that when we get to the actual simulation. And the number 10 should be comments, not conclusion. Sorry, that was a typo. The lab report does have a rubric. Well, it should have a rubric. Okay, it will have a rubric. I apparently did not get that on here either, but there is a rubric for it. So I'll get that posted up here. So now let's look at the instructions for doing this. I'm going to click on the link redox simulation. And a PDF file is going to load up. And hopefully you guys can see this. Jamie, are you able to see things okay at this point? Or are you not seeing it? You can text if you're not seeing it. Ah, good. Okay, far out. Then let's get back to it. So oxidation reduction virtual lab. In this lab, you will explore reactions between metals and ionic solutions. And we've got here a generic equation. So we have A solid, that's our metal, reacting with BX aqueous, that's our ionic solution. And if they react, you're going to now get B not as part of an ionic compound, but B as a solid metal. And you will also have produced a new ionic solution that the ionic compound is AX instead of BX. So it says below that in this example, a reaction will only occur if the thermodynamics favors B being a solid metal rather than A being a solid metal. And a little story on that. This has to do with like white jewelry is made of things like gold and silver and platinum. Because you don't want it to tarnish, you don't want it to oxidize. You know, if you get a gift, ladies, of a nice jewelry item and it tarnishes, you won't be real happy about it, right? So, like when I was in high school, I was dating somebody. She was wearing a choker. It looked like it was silver, but no, it was not. It was a really warm night. We were at a dance. Everybody, it was hot and all that stuff. Anyway, she wound up with a green ring around her neck. So that was not made of silver. It was made of something else, which was easier to oxidize. So anyway, going on. Therefore, for some combinations of AS and the ionic solution, no reaction is going to occur. That's because A wants to stay solid. It does not want to become part of a ionic solution. It does not want to ionize. It does not want to oxidize. So when a sample of a solid metal is placed in a solution of BX, if a coating is observed, then a reaction has occurred. If you don't see a coating on the outside of the metal, which is the new metal, then there's not been a reaction. So to observe some reactions, a simulation is going to be used. You begin that by clicking on this link, and then you may need to activate Flash in your browser depending on how you have your security settings set up on your browser. And then it goes through here how you're going to do it. I'm not going to read all that stuff. I'm just going to show you how it works. So I'm clicking on the link. And this is the simulation. So what they did here was they had a solution of copper nitrate in the lower, in the beaker. They put in a piece of zinc. Well, zinc is okay with becoming an ionic compound. Copper, on the other hand, does not want to ionize. It does not want to oxidize. So it's going to stop being an ion and it's going to start being metal. So that's this orange color material we see on the metal that had been put in the solution. That's where we have converted the copper 2+ into copper solid. Now to do our simulation, we click on where it says start, and it says here are some beakers of aqueous solutions of labeled compounds. So we're testing 8 different solutions, and we're also going to test 8 different metals. So to do the first part of your lab, you're going to click on activity 1. Now you see 4 of those beakers, and you see 4 metals. So we got magnesium, copper, zinc, and silver. We got magnesium nitrate, zinc nitrate, copper nitrate, and silver nitrate. So we need to pick a solid metal that we want to put into the solution. So I'm going to pick copper. So now you can see there's 4 pieces of copper. Each one's going to go in a beaker. We click on the blue box, and it's going to lower them down into the solutions. Now you notice that over here on the right, the solution is changing to a greenish color. It was originally clear. Notice that the one that's out, sort of a greenish blue, doesn't change. And we've gotten a message here at the top that says you can remove the metal from the solution and record your observations. So I'm going to click here on the blue box. It's going to take them out. Notice that these 3 pieces of copper do not look any different. That's because the copper wants to stay copper solid, and the magnesium and the zinc and the copper, well, the magnesium and the zinc, they're not going to deposit because the copper wants to stay. But on that last one, which was originally silver nitrate, silver wants to be the metal more so than the copper. Therefore, we're getting an accumulation of silver metal on the outside of the copper bar that we put in there. We're going to repeat this for other sets of materials. And then the last one is the reactivity of certain metals in hydrochloric acid. So I'm going to go back to where I'm sharing this with you. I'm going to stop doing that and ask, does anybody have a question? Okay, we're going to do this as groups, and I don't know if I've got everybody in their groups or not. Let's see. Um, oh, okay, there's a few people I need to move around. Give me a second and I'll do that. Okay. Um, yeah, I think I have everybody. Oh, okay, Diane, what's up? Do you want to talk or chat?
So after our lab, are we all done?
I'm sorry, what did you say?
Like if after our lab, like after doing the lab simulation, like
Can
are
you
we
leave? Yes,
are we gonna
yeah,
go?
yeah, yes, you can leave whenever you have the simulation completed.
And for the observations, like for example, observations if there's like precipitation or color change, right?
Right. Yeah. The observation you're looking for mostly is that accumulation of some metal on the outside of the metal strip. So that would be a reaction. If you don't see that, it'd be no reaction. And then in some cases, the color of the solution will change, but in some cases it doesn't because it doesn't have a color, so you wouldn't see it.
Okay, thank you.
You bet. Okay, I'm going to go ahead and hit the start button. Now remember, if you have a question while you guys are working on this, you can just chat back to me and or the main room, and I'll be here. I can answer those. And then whenever you guys get done, just just chat me, let me know, and then I'll say see you later. So okay, here we go then. I'm going to hit start.